Hello and welcome to the AWS Innovate Online Conference AIML edition. My name is Glenn Gore, I'm the Lead Solutions Architect for AWS. And I wanted to kick off this very special edition of AWS Innovate by focusing on the impact that artificial intelligence and machine learning is having on the world around us and how we think about this technology. Before we get started on AIML though, I want to just talk about the event itself. We've been running the AWS Innovate Virtual Conference for a number of years, and it's always been a highlight of mine to bring the team together in Singapore and where we live produce the event and then repeat it in multiple time zones around the world. Unfortunately, this year we've had to change the format slightly due to the impact of coronavirus. We're hosting this Innovate event from two continents, the US and Singapore. And thank you for over 150,000 registered attendees. So please stay safe out there, everyone. Now, when you reflect on the evolution of machine learning services over more than the last 20 years, I'm seeing a rapid increase in the sophistication of both the underlying AI/ML technologies as well as the creative ways that businesses around the world are applying AI/ML services to provide new capabilities that can help grow revenue and or reduce costs of certain tasks, such as the use of intelligent chatbots to reduce call center calls for common use cases, such as changing addresses, for example. Now in 2020, we really are entering a new golden era of machine learning. The ease of building sophisticated applications on top of the AI/ML building blocks makes it easier than ever for builders to build the future of tomorrow today. And this is really the biggest opportunity for each of you. The innovation that AI/ML enables is everywhere, as well as the opportunities for you to learn and build and put this into practice. Now, customers are using artificial intelligence and machine learning in industries ranging from healthcare, for example, where GE Healthcare have embraced machine learning to provide better patient outcomes through looking at the quality of care algorithms that predict the possibilities of post-discharge complications in patients. Now, GE Healthcare, they've created custom algorithms and models that work with existing X-ray and CT scan data, as well as other data sources such as patient-reported data, sensor data, and numerous other sources. And this allows the algorithm to recognize the difference between what is a normal and abnormal results, for example. And in a recent survey, they discovered that actually already 82% of healthcare decision makers say that the use of data is already resulting in improved patient care. Actually, every industry is leveraging the abilities of artificial intelligence and machine learning in both direct and indirect ways. From smarter fraud detection and management solutions for the financial services industry, through to a new generation of robotics, automation, and connected devices in manufacturing, retail, and energy sectors. It's this combination of human creativity and the raw processing capabilities of machine learning at scale that are incredibly powerful. And I can't wait to see what each of you build. Now, before I hand over to Olivia Klein, our Head of Emerging Technologies for Asia Pacific, I'm going to play a real-world use case of how Formula One are using AWS AI/ML services to provide deeper insights into the world's most technical and data-driven sport, the incredible world of F1 racing.
Formula One is absolutely the ultimate blend of man and machine. There's no other spectacle on earth that blends the human talent and the technical talent. Once we put that racing driver in the car and he pulls out the garage, he's got to deliver millimetre perfection, and equally when the car's back in the garage or we're back in the factory, we're delivering, as engineers, millimetre perfection.
Your key performance index in a Formula One car, your main performance differentiator is aerodynamics. So in order to understand the aerodynamics, what we had to do was we went from one pitot sensor, a sensor that measures dynamic pressure on the racing car, to covering the whole surface of the racing car with around about 100, what we've got in the car now. But what did that do? That then gave us an explosion in data channels. So we went from maybe around about 100, 200 data channels in the mid-90s to about 1,000 that we've got now, and that's growing all the time. Every time we think of something new, every time that the rule makers throw something out as well, we need to understand it better, then we need more data. And what that means is that you can see from around about 2010, there's been an absolute explosion. It's gone from something like 2 megabytes per lap to 40 gigabytes per lap. That's a huge amount of data that we're generating. That's every single lap, every car.
There's so much onus on humans to make what are sometimes overwhelming decisions, and if you can have technology that augments those decisions, then that's something that is just amazing. And I think that this partnership between Formula AWS in bringing machine learning and bringing artificial intelligence into Formula 1 and allowing the fans to consume that is incredible.
Let me show you something that we've already done on the SageMaker platform. This is an example of Lewis Hamilton. He's behind Sebastian Vettel, who chooses to pit. At this moment in time, Sebastian Vettel team, Ferrari, have to decide whether or not to pit. Let me tell you, having been in that situation many times, that's a stressful situation. But by using ML, by using the SageMaker platform, we're already predicting during that lap what's going to happen. So we're predicting here that he's going to come out 6/10 behind. So Sebastian Vettel shouldn't in fact pit at this moment in time. And just as Sebastian pits, and you see it right here now, he gets pulled into the pits, ML technology is predicting that he's going to be 1.8 seconds behind. He makes a pit stop. The pit stop's absolutely fine. When he emerges on the track, there's Lewis Hamilton, crosses safety line. There's Sebastian Vettel, crosses the same line, 2 seconds behind. Exactly as predicted by the technology.
It's hugely exciting to be a builder of new technology. You know, that's a key aspect, I think, of the partnership between Formula 1 and AWS. We're bringing artificial intelligence into Formula 1. It's something that I've been a key advocate of, you know, absolutely passionate about for a number of years now. We're the most technologically driven and data-driven sport in the world. We rely on analytics for self-improvement every minute of every day. And the point is that we need to somehow bring that to the general public. You know, it's about trying to do something for Formula 1 that is bigger and better than just making a racing car go a little bit faster. It's trying to put on a bigger and better and greater show, and to be part of the journey is an honour.
Thank you, Glenn. That was really insightful to kind of see how AI and machine learning is really applicable to any kind of different industries. And really, we see an evolution of how machine learning is being applied thanks to cloud computing services such as AWS. But having said that, our mission really is how can we put AI and machine learning into the hands of every developer out there. And this vision is a bit multifold. So we want to provide you with a variety of different services, from all the way of fully managed AI services that are just an API call away, all the way to machine learning services that allow you to effectively train your own machine learning models yourself. We're going to dive into the details of that. Lots of different frameworks in this space that make even deep learning right now really easy for developers to apply and build their own deep learning models. And we're also going to have a look at the infrastructure when we train machine learning models, but also when we make predictions with those machine learning models. So let's kick it off and have a look at the fully managed AI services first. What do I mean with fully managed? Well, there are a variety of different services in the space of computer vision and speech and text and search, all the way to personalization or fraud detection or forecasting or code development, contact centers or chatbot functionalities. All of these services are available and they're fully managed and trained by AWS, and you just need to make an API call to get access to their capabilities. So if you take something like Amazon Recognition, it allows me to analyze image and video material, detect objects and activities or individuals, and understand faces, for example, all the way to speech. If you want to render lifelike voices, Amazon Polly allows me to do that. If I want to transcribe voice conversations, for example, of a phone call, Amazon Transcribe allows me to do so. If I want to analyze text, understand sentiment, and understand what's being written about, Amazon Comprehend is a natural language processing service fully managed. Amazon Translate allows me, obviously as the name indicates, to translate between different languages. Amazon Textract allows me to understand documents like PDFs or image materials and extract intelligently the information that we have in those documents. Amazon Kendra allows me to have search functionalities for my own company, for my own enterprise. So index information of my internal information, and again use the natural language way of searching things to understand what's going on. With Amazon Personalize, you get access to the same personalization and recommendation techniques that Amazon.com is using. without the need to have any machine learning expertise. You just make a few API calls. The same goes for Amazon Fraud Detector, which allows us to understand, for example, fraudulent online transactions. A lot of learnings that came from the broader Amazon.com company that we now provide you as a fully managed AI service, just an API call away for you. Same goes for Amazon Forecast, as the name indicates, allows us to actually get access to forecasting AI services without the need to have machine learning expertise. Amazon Code Guru allows us to understand and analyze the code that we're developing, profiling it, and understand, maybe where could we have better efficiencies around writing code, or how certain segments could be optimized, or find certain problematic kind of pieces of code where you might be using access codes that you shouldn't use. Contact centers with Amazon Connect with Contact Lens, we allow an intelligent AI-driven contact center where we understand the conversations and sentiments and really understand this better without relying on the agent logging this information down into our CRM system, all the way to Amazon Lex, allowing us to build chatbot functionalities with just a few clicks of a button. So the AI services really allow us, with a few API calls or a few clicks of a button, get access to these fully managed, continuously trained and optimized AI and machine learning services. Now, we should always start there, but sometimes we want to build more specific machine learning models that are specific to our company. And this is really where the machine learning services come in. So let's have a look at the machine learning services, and specifically also the Amazon SageMaker service and feature functionalities that we have, and understand how that works. But before we dive into that, let's first understand the machine learning flow. If we want to build a machine learning model, make use of it, and actually make predictions with it, what does a general flow look like when it comes to machine learning? Now, I'm a solutions architect myself, so my preferred way of actually trying to understand the flow is to use a whiteboard. Now, I got an intelligent whiteboard here with me, so what I'm going to try to do for you is kind of draw out a machine learning flow on how it would look like. Now, machine learning generally always starts off with data. So we have data that sits somewhere. This can be transactions or different information or information from our P system or user click streams. No matter what it is, we want to store data somewhere. From there, we generally go into a certain flow. That flow then starts off by saying, I first want to build a machine learning model. Right? That's the first thing that we do. What are the kind of algorithms, for example, that we want to train our machine learning models on? Maybe I want to use the AWS Marketplace to understand, what kind of algorithms are available there for me. I also want to have the abilities to explore my data, very often with the help of so-called notebooks. Now, the other thing about data is this might be raw data. So one other capability that we're generally looking at here too is, can I actually annotate or label my data sets, right, before I actually start building that machine learning model. Now, the next iteration, when we go in a set and we say, okay, we have an algorithm, we want to train my machine learning model. That is really the next phase. So the next phase is really, I want to train a machine learning model here. And again, the idea here is, what do I want as a developer specifically, or even a data scientist? I want to have a platform that with one click of a button allows me to train my machine learning models. We're also going to look into how can I maybe tune some of the hyperparameters. So tuning is a very important component here too. The other element that we're looking into is probably also debugging what's going on. Sometimes there are problems with the training, and we also want to experiment, right? We want to run experiments with different models that we train on top of the platform. Now, the next step, if we're happy with our model and it looks good, the accuracy is great, we're going to look into deploying that machine learning model out. And when I say out, well, where could it sit? Sometimes that model might sit in a cloud environment. In this kind of scenarios, we want to have APIs that allow us to infer, make predictions from that machine learning model at that very moment with A/B testing and versioning, etc. And we also then obviously want to monitor that machine learning model, continuously see how it interacts with the ongoing users that operate on top of it and the predictions that we make. The other thing, of course, also, I want to have the ability to do that with one click of a button. Right? Click of a button, I have it deployed out, and maybe it doesn't go to an API, maybe it goes to a hardware device. So we also want to have the ability to potentially deploy this out to hardware at the edge. Think, for example, IoT kind of use cases. And from there, we then really start making predictions, or very often called inference, or infer from it. And here it can really be either way, that we say, okay, predictions are good, threshold is great, or sometimes we say we reach a very low prediction score here, so we also want to have the ability to have a manual review of the prediction that was made and send it back to a human for review. In addition to that, in certain use cases, we might want to say, actually, the build and train phase, I'm not completely comfortable to do that. So you also have the capability of saying, I sometimes want something called AutoML, automatic machine learning, where I ingest the data, it automatically tries to find the machine learning models, and then I'm ready to deploy that out. So those are kind of the capabilities that we're looking for and the overall machine learning flow. Now, if you look into the AWS services, you will find that all of this here pretty much is taken care of by the Amazon SageMaker service and its capabilities, in which I'm going to dive in a little bit. And obviously our data generally is stored in an S3 environment, so we want to build our data lake on top of Amazon S3. So if you look at all of these capabilities, SageMaker and Amazon S3 here really helps me to get a hold of it. So if I look at the overall Amazon SageMaker capabilities, we really can help with preparing, building, training, and tuning, and deploying and managing your machine learning models with things like Amazon SageMaker Studio and Autopilot and notebooks and ground truth to label it and one-click training and one-click deployments and automatic model tuning, all the way to debugging it or experimenting with it or deploying it out to the edge. Now, I want to dive into some of these specific features and functionalities of SageMaker in a little bit more depth to understand how they apply to us. The first part is really the IDE. Amazon SageMaker Studio allows me to have that fully integrated development environment for machine learning. So easy to collaborate with different data scientists or machine learning experts and kind of run a variety of different experiments, try to understand and debug kind of what we're working on, and with a few clicks of a button, send it off to training and deployment itself too. How would an interface look like that? Here we see, for example, a screenshot of Amazon SageMaker Studio, where we have a notebook on the left-hand side, and we have a bit of an evaluation of experiments that, for example, run on the right-hand side here. So a great way to kind of have an integrated IDE for all my machine learning needs. Now, I mentioned earlier AutoML. Sometimes I don't actually want to choose an algorithm and build that kind of machine learning algorithm. I just want to submit the data, and I want machine learning to find the right kind of machine learning algorithm. And that's really why we launched Amazon SageMaker Autopilot, which allows me to automatically create machine learning models based on your data, right, which comes in a tabular format, and then we kind of try to find the right kind of machine learning algorithm and give you a variety of different iterations on top of those machine learning models and algorithms that we produce, and obviously give you an objective score. So what is the precision that we kind of get out of these different algorithms. Again, this is not a black box though, so we propose to you the different machine learning algorithms that we use with a certain accuracy that comes with it, but it also then comes with a notebook that gives you full control over the source code of that machine learning algorithm. How would it look like if I actually put something through SageMaker Autopilot? I see here, for example, a variety of different autopilot jobs that are running through with a certain objective on the right-hand side that indicates which algorithm or model here would probably perform best. Now, also mentioned earlier, we sometimes need to annotate data. That is really where Amazon SageMaker Ground Truth comes in. So Amazon SageMaker Ground Truth allows me to take raw data and have an interface where I can now annotate that data. But not only is it an interface that allows me to do things like image classification or draw bounding boxes on pictures or do semantic segmentation, and we have also automated semantic segmentation, classifying text, etc., or even your custom annotation model, but it also comes with a logic that tries to learn from the way you actually annotate your data. If it can then automatically annotate your data, it will do so, and if it can't do that, it will go back to those human annotations. So SageMaker Ground Truth will learn on how you annotate the data, and if it repeats or the same kind of data points come back, we might be able to automatically annotate them or otherwise fall back to human annotation, effectively reducing the cost that data labeling takes, and as such also the time with that. Now, if we choose not to use autopilot, we might want to actually build our own machine learning algorithms. But before we get to that, we should have a look at the inbuilt algorithms of Amazon SageMaker. So we provide you with inbuilt algorithms that are optimized for scalability, so you can run it and train it on multiple kind of SageMaker nodes or different GPUs. And these models, or these, I should say algorithms, really are varied from things like classification or clustering, to forecasting, to topic modeling, lots of computer vision, inbuilt algorithms that are there for you, regression algorithms, or working with text or translation. So this is always a good start to say, is there an inbuilt algorithm that SageMaker provides me with that could actually help me solve my problem? And if those inbuilt algorithms aren't enough, you should have a look at the AWS marketplace for machine learning, where our partners provide you again with different kind of machine learning algorithms that can be loaded straight into SageMaker and trained in your own SageMaker environment, or even with fully managed models, or even data points. So the AWS marketplace, some partners even provide you with data sets that you can use for training your own machine learning models without the necessary need to maybe write your algorithm or have those data points available. Again, a huge variety of things like OCR and computer vision and ranking and handwriting and recognition, many different areas. So check out the AWS marketplace and see if there might be an algorithm available for you to get started quickly without the necessary need to write your own machine learning algorithm. The other thing that we have with machine learning is that machine learning algorithms and models generally have a variety of different parameters, very often referred to as hyperparameters. If you take things like a decision tree next to Boost, this might be the depth of the tree or the amount of nodes that we have on my gamma. Or if you take a neural network, that might be how many hidden layers do we have in our deep learning neural network? What's my laning rate? What's my embedding dimensions or the dropout rates? These are all parameters that are sometimes it's hard to make the right decision on what should this parameter be set to. And so one of the techniques that you can do is to say, let me experiment with multiple of those parameters. Now, you don't want to do that manually and go one by one and run different kind of parameters all the time. And that's really where automatic model tuning comes in. And SageMaker provides you with those capabilities, sometimes also referred to as HPO, hyperparameter optimization. So it will try to run through a variety of these parameters and see which parameter then performs the best, so where we can get the most accurate model out of it. Again, that's obviously fully managed and automated as such, so it makes it really easy for me to kind of say, SageMaker, please find me the right parameter for the optimal kind of accuracy. And talking about, experimenting around with things, if we build different kind of machine learning models, we also want to understand, could we actually experiment with different models and see how they perform? And that's why we introduced Amazon SageMaker experiments, which allows us to really organize, track, and compare different kind of machine learning training experiments that we're running and get a better insight into which one might perform better over time. And obviously we can do this over time, so it's not always just a snapshot in time. Over time, you might want to run a variety of different experiments on new kind of data sets. How would that look like in the SageMaker Studio experience? Well, obviously it allows us to run a variety of different experiments, run those training jobs in parallel, and then see which one performs better, and of course then start to kind of plot out different kind of parameters or objectives that we're looking for here, and decide which model now performs best. So a great way to quickly experiment at the same time. And machine learning often is a bit of an experimentation, right? We have a rough idea or hypothesis of where we want to get at, but then we can experiment with different kind of ways of achieving a certain outcome and see which one works best. Now, the other thing that you find is if you train machine learning models, especially deep learning models, these can be computationally very extensive and sometimes might run for hours. I talked about learning rate as one of the hyperparameters earlier. Sometimes if you set these parameters wrong, your model might never converge, and it might train for hours and hours until it just finally shuts off because you put a maximum kind of training time to it, and then you realize actually in the first 10 minutes the model went so far off it will never converge, and I just wasted 10 or 24 hours of training time that went nowhere. So how do we actually get better insights and access into when we train these machine learning models? And that's really why we created the functionality of Amazon SageMaker Debugger. And that allows us to analyze and debug or explain or even have alerts around the way we train machine learning models. So as the training occurs, we can set certain rules or have certain automatic error detection, and maybe then take the decision to actually shut off the training and bring it back and say, well, we're not quite ready for the training yet. Model was set incorrectly, the algorithm was set incorrectly. Again, integrates nicely and well into the Amazon SageMaker Studio experience. So if you have a look here, for example, you can see on the right-hand side that certain issues were found, so the debugger identified things like vanishing gradients or an overfitting of the model after just a few minutes, and that's great because now we can take the decision to maybe cut it off, change our algorithm or our model around before we keep retraining it. So debugger really allows me to find those problems as they occur during training, rather than seeing training as a black box where I shoot it off and I wait till it's fully trained, and it might not have been the right way to train it. So a great way, again, to be a little bit more productive and effective in the way we build our machine learning models. Now, talked about experiment and tuning and so on. What if we deploy my machine learning model out? And this is really important because machine learning models that might perform great today might not perform great tomorrow because things are changing or users are changing, etc. So we constantly need to monitor how our machine learning models operate. And that's also the reason why we launched the functionality of Amazon SageMaker Model Monitor. Now, Model Monitor allows us to continuously monitor these models in production, set certain rules, and even have a visual data analysis to understand how these models perform over time. And maybe over time they might perform more poorly, and that indicates maybe a way to retrain it or change things around. So again, a great functionality to make sure as we run machine learning models in production that we constantly monitor it and understand that we run that model optimally as we want it to run. Having said that, if we talk about machine learning, we never predict always with 100% score. Actually, if that is the case, we probably have an overfit model, which we don't want to have. So we generally talk about a certain precision, we talk about a certain accuracy, and then we often talk about a certain threshold. If an accuracy is too low, my prediction isn't good enough. And what do we do in that case? In that case, we often want to have a manual verification. And this is really where Amazon A2I comes in. So A2I allows me to actually have a manual human review if my threshold falls below a certain score. And this works both with fully managed AI services here, but also custom machine learning models that we're building with Amazon SageMaker. So if the confidence score is really high, it obviously just passes through, we make the prediction, everything is great. But if the confidence score is low, we can push it back for human review. So if we take a fully managed AI service such as Amazon Textract, well, A2I could, for example, look like this, where Textract tries to extract certain key value pairs here. Here would extract the name, and if that name would be extracted with a low threshold and Jane might have been detected as J-A-U-E instead of Jane, this can be sent for manual review. The interface then of A2I allows me to then say, yeah, actually either way it's right or it's incorrect, and it allows me to obviously correct it as such. So I have that manual human review. Again, it works with any of your models in SageMaker and with some of our fully managed AI services. Now the other thing, if we have a machine learning model that we deployed out into production, very often we also look into how can we apply that maybe on ongoing transactions in my database, for example. If we want to integrate our machine learning models with my database, it can be quite cumbersome. We need to write applications that talk to each other. And so we recently also launched the capabilities to actually infer your machine learning models from Amazon SageMaker and some of the AI services such as Amazon Comprehend straight away using SQL language on services such as Amazon Aurora, Athena, or QuickSight. And that makes it really handy because now, as a developer, I might feel very comfortable running SQL queries, but it was quite complex for me to figure out how do I actually bring that back to my machine learning model of what I just queried, etc. With this integration, it can look as simple as the following examples. So let's say, for example, I want to find suspected fraudulent transactions and only insert them into my approved sales table here if it is not a fraudulent transaction. You can see at the bottom I have an if is transaction fraudulent. This would be a SageMaker model that I custom trained and that is now being inferred, and only if that holds false, I would actually insert that kind of item into my table. So straight into that SQL query. And you can also call fully managed AI services. So I talked about Comprehend earlier. Here in this scenario, for example, I can say I want to select product reviews, but only where the sentiment is negative. With AWS_comprehend detect sentiment here, we're making a call to the fully managed AWS AI service here, understand the sentiment, and then only return the product reviews that have negative reviews. And you can even use that in the capability of ordering. The predicted future spend here on the right-hand side, again, is a custom model that we are running in SageMaker, and we say order it by what that predicted future spend is, and then give me a top scoring of my predicted future highest spend customers, for example. Again, making it really easy for me as a developer to use the SQL language that I'm very familiar with, whilst integrating it with my machine learning models. Now let's talk a little bit about frameworks. So if I really go down the path and say I want to build my own custom machine learning algorithm, and sometimes that does make a lot of sense, I would still encourage you to look into the variety of different frameworks that make this much easier, especially when we talk about the deep learning space. A lot of frameworks have emerged to make this a lot easier. No matter if these are frameworks like TensorFlow or AmaxNet or PyTorch or Caffe or Chainer or Onyx or integration components such as Keras or GLEEN, they make it really easy to kind of get started with deep learning and machine learning with those frameworks. Now, from an AWS perspective, we always want to give you choice and flexibility of what framework you want to use. We are agnostic to the framework you want to use, so any of these frameworks listed here, but pretty much any framework you want to run can be run on top of AWS. And if you run them in SageMaker, then they are fully managed, or if you choose you want to run it on top of EC2, you can run it yourself. I encourage you to look into our deep learning AMIs, armies, or into our deep learning containers. Why? Because they come with optimized versions of these frameworks and optimized libraries on the underlying operating system. Now, it is really important that you have these optimized versions because they give you a much better performance. Let's take, for example, TensorFlow. Now, if you run TensorFlow on top of EC2 and you use that optimized framework, you get a much better performance. We benchmarked this on a very common benchmark, specifically on training a ResNet 50. ResNet 50 is basically computer vision, a model that we're training on millions of images of the ImageNet library. Now, if we use stock TensorFlow, so I just do a apt-get install or sudo yum install on an EC2 instance, I get a certain kind of performance, but it doesn't scale very well, especially if we say we have multiple GPUs, multiple nodes, we want to scale it out. If you use these optimized kind of frameworks here that come with those armies or come with SageMaker or come with the deep learning containers, you get a much more linear scalability. So in this kind of scenario, we found that when we trained ResNet 50 on 256 GPUs at the same time, scaling efficiency was only 65%. With the optimized version, we got a lot closer to linear scalability with 90%. And as you can imagine, the training time as such went down from 30 minutes to 14 minutes, which is actually the fastest time of training ResNet 50 on TensorFlow. And of course, less training time means less cost. You only pay by the second of what you use when you train it itself. Which brings me to the point of infrastructure. If we want to train a machine learning model, or if we want to make a prediction from a machine learning model, what is the right kind of underlying infrastructure that I want to choose if I do not use one of those fully managed AI services that abstracts that away from me? So let me start off first by kind of outlining the different kind of areas that we will be looking at here. So is it a CPU, is it a GPU, and is it an FPGA? What is the right kind of infrastructure here, or underlying infrastructure that we want to use? So CPUs are interesting in the sense that they're great for general purpose computing. Generally comes with tens to maybe hundreds of different processing cores. GPUs, on the other hand, are really great by having thousands of different processing cores and are highly effective at parallel executions of code. And the same goes for FPGAs, field programmable gate arrays that comes with millions of those programmable digital logical cells, which again have hardware time parallel execution. Now, if we think about training a machine learning model, parallel execution can greatly speed up that training. So GPUs and FPGAs are generally much more of an advantage when I train a machine learning model. And now you might wonder, well, why is that? Well, if you fundamentally look at what training a machine learning model is, it's fundamentally lots and lots of matrix multiplications that we do, coupled with extremely high memory bandwidth requirements. Now, GPUs with their thousands of cores that can execute these multiplications in parallel are optimally suited for training a machine learning model because we do all these matrix multiplications all the time over and over again. So if I now want to choose an EC2 instance type, either way because I train it on AMI or a deep learning container myself, or even when I use SageMaker, I have the flexibility to actually choose my underlying instances for training. Well, for training, we probably want to look into the P3 instances, which is the GPU compute instances available for you. And with the largest P3 instance, we get up to 8 NVIDIA Tesla V100 GPUs, offering us up to a petaflop of computational performance and up to 300 gigabytes per second GPU to GPU communication. So really great to train your machine learning models because lots of performance in parallel, so lots of these matrix multiplication happening very quickly at the same time. And we also released the P3DN, which is the most powerful GPU instance in the cloud. Comes with 100 gigabit per second, of networking throughput. The 3 instance is really great if you want to build clusters or HPC simulations, but also great when you load up data. So think about, a data lake that might sit in your Amazon S3 a bucket. Now with those fast networking capabilities, I get access to that data fast, can load it up fast, and run my training jobs itself. Now, there is a bit of a misconception though. So very often we look at training, computationally intensive, and we think that might be the most expensive thing to do. Training must be expensive. Running my machine learning model can't be so expensive. Well, the reality is and what we found with most of our customers, we don't train 24/7. And when we train, we generally exhaust the capability to the max, right? We're up to 100% utilization of those EC2 instances that we use while we're training, and when we're done training, we shut it down. Now, when we make predictions, on the other hand, that is something that might be running 24/7. Right? I might need to make predictions all the time. However, let's say if it runs on top of my platform, I might not always have the same amount of traffic of my users that go against my platform. So I have the typical kind of elasticity that I find otherwise in other components in cloud computing, now also with machine learning. So if I make a prediction and I still need the GPU capabilities, can I reduce the granularity of these GPU increments that I have? Because even if I choose the smallest P3 instance, maybe my platform doesn't have that much traffic at any point in time, and I don't actually use the 100% of those capabilities, yet pay for it. And so we thought about it, and we're thinking, how can we make this easier for our customers? How can we make it more cost-effective for our customers to get GPU capabilities, which are very useful in the machine learning space, very useful in the deep learning space, but in much, much smaller increments? And that is the reason we launched something called Amazon Elastic Inference. Elastic Inference allows you to reduce your deep learning inference cost by up to 75%. Why is that? Because it allows me to attach and detach GPU capabilities to EC2 instances, or to, let's say, for example, my SageMaker environment in very, very small increments. We're available from 1 teraflops all the way to 32. Now that allows me to be a lot more elastic, right? Attach and detach these capabilities as I need more or less kind of performance for my inference, because I have more or less traffic against my platform, or more throughput of information that I need to make predictions against. Again, allowing me for a lot more elasticity around how I make those predictions. The other thing though is even if we look at EC2 instances themselves, what should we choose when we talk about inference, when we make predictions, right? For training, P3 might be just the right thing, and the P3DN, the most powerful I want. But when I make predictions, I might want to choose a few other ones. So that can be all the way from CPU-based instances, which are very useful for smaller kind of models, or models that have a low sensitivity to performance. So C5 instances might be ideally suited here. If I need more GPU-based kind of instances, so if I have applications that require access to things like CUDA or CUDA DNN libraries or TensorRT libraries, then I probably want to use GPU-based instances. If I make an inference, probably G4 instances might be just the right type of instance that you want to use. But we also recently launched the so-called EC2 Inf1 instances. And these instances come with the AWS Inferentia chip, which is a custom chip that we built that is specifically optimized for performing machine learning inference, so making predictions on top of EC2s. And actually we find that it has the best price performance for machine learning inferencing, finding up to 40% lower cost and up to a 3 times higher throughput than G4 instances. And you might wonder why some of that is, and so I wanted to go into a little bit more depth here. And what we find is that when we make an inference with a machine learning model, sometimes the memory footprint of that machine learning model can be quite large, especially as the models get a little bit more advanced and complex. Take something like a natural language model such as BERT. The memory footprint is actually 680 megabytes. Now that doesn't fit into a single custom chip, and what that results in is that we always need to load the model from DRAM. With AWS Inferentia, we actually came up with something called AWS Inferentia Cascade Mode, where we are able to actually do a distributed caching of that model across multiple cores, effectively allowing us to reduce the loading of the model from that DRAM, so that loading and offloading of the model itself, effectively obviously reducing the time that it requires to make those inferences. And as you know, in a cloud computing environment, less time also means a lot more cost effective, so faster and more cost effective as such. Now, how can you use these AWS Inferentia chipsets? Well, actually we have something called AWS Neuron. AWS Neuron is actually an SDK that comes with a compiler, runtime, and profiling and debug tools that allow us to take a model from a major framework, so TensorFlow, MXNet, or PyTorch, and compile it for the AWS Inferentia chip. How can that be used? I wanted to give you an example. Take, for example, the Alexa voice services. If you have an Echo device like the one shown here, how does that normally work? Well, if we call the wake word, which the default one would be Alexa, that machine learning model actually runs on the device itself. But after that utterance, we basically go to the Alexa cloud service. So the different commands, requests that we might send to the Alexa cloud service platform actually done in the Alexa cloud service where we make predictions. So this would be multiple models, so from automatic speech recognition to natural language understanding to understand your intention and the skill that you actually want to call and what your intention is, to all the way rendering a response using our text-to-speech model. Now, the reason I wanted to show you this is because there's a lot of complexity in this. Take, for example, just the text-to-speech component. So we went through the entire thing of understanding what you're saying, understanding what you want to do. The moment we're ready to render a responsive text-to-speech component, to render 1 second, we actually require 90 gigaflops of operational power. Now, we actually, when we start this off, we ran that on GPU instances and recently moved to the inferential chipset, tremendously actually reducing the cost of just rendering these response times back. So I really encourage you to look at AWS Inferentia as an additional capability when you want to make machine learning predictions and inference of lowering the cost and actually having a higher throughput itself too. Now, I mentioned the Alexa voice service, for example, that initial inference is done on the device itself. We often find in the IoT space scenarios where we want to make machine learning predictions on the device itself. So how do we actually move a model onto different kind of pieces of hardware? And that is why we came up with Amazon SageMaker Neo. So you train your machine learning model once in a SageMaker environment, for example, based on your MXNet, TensorFlow, or PyTorch model. And by the way, we also allow for XGBoost. And then Amazon SageMaker Neo compiles and optimizes actually, so we have a better performance, compiles it for different kind of pieces of hardware. So no matter if you want to run it on Intel or NVIDIA, maybe on Qualcomm or Cadence, or on ARM, for example, on your Raspberry Pi, all the way to Xilinx. So that's really useful when we say we train a machine learning model in my cloud environment, but then I push it out to devices that might sit at my edge location. We actually launched AWS Deep Lens and AWS Deep Racer and AWS Deep Composer. I wanted to have a quick look if you never had the chance to actually see those devices. If you look at, for example, AWS Deep Lens, this is a device that allows us to really get hands-on with computer vision. So it comes with a wonderful wide-angle camera here, and then allows me to run computer vision model on the device itself. So those predictions are being made on the device itself. We train it in a cloud environment, then push that model out here. By the way, if you're interested, it runs obviously AWS Greengrass under the hood to actually publish these models out to the Deep Lens device itself. Now, what about reinforcement learning? So for reinforcement learning, again, we wanted to put that literally into the hands of the developer and actually create a little bit of a competition around, and that's why we launched the AWS Deep Racer. Here, for example, you see the first iteration of the AWS Deep Racer comes again with a camera and then runs the reinforcement learning models on the Deep Racer itself. Underneath, there's obviously a racing car here, and we have lots of competitions, the Deep Racer Challenge that you can participate in, including one right now here for the AWS Innovate Conference. This is the first version of the AWS Deep Racer. And on last AWS reInvent, we also launched the Deep Racer Evo Evolution, the second generation. If you allow me just to take off the hood here for once, you can see that it now comes, the newest iteration comes with actual 2 cameras, so stereo cameras here, allowing again for more interesting kind of competitions in the Deep Racer challenges. But also if you look on top here, we have a LiDAR sensor that allows us to detect objects that surround us. So again, a great way to kind of come up with even more interesting Deep Racer challenge competitions. And then lastly, in the space of generative excuse me, generative adversarial networks, GAN networks in general. So kind of use deep neural networks to create new artworks or create new music. We wanted again to kind of put that into the hands of every developer, and that's the reason why we actually launched AWS Deep Composer, which allows us to actually compose music, and we're going to have a breakout track later that goes into a little bit more detail, and then with the help of deep learning allows us to create music with different styles and create new kind of styles based on the music that we just played. So great ways to kind of get hands-on with some of these newer deep learning technologies in a bit of a playful manner. Now with that, I hope this was insightful to kind of dive into the further details of the platform, from AI to machine learning service to frameworks and infrastructure. And I'm going to hand it back over to Glenn to close up. Thank you.
Thanks, Ollie. Always insightful hearing from you on the use cases and patterns of deployment of the AI services. I really like the talk you gave around SageMaker, because SageMaker continues to be one of the core services for tens of thousands of our customers to deploy their artificial intelligence machine learning workloads. Actually, SageMaker have been putting a lot of investment through, whether it be SageMaker Ground Truth for managing your data sets, through to SageMaker Experiments to capture and compare the results of your own experiments, or to SageMaker Neo, which allows you to take your AI/ML workloads and deploy it to a variety of end devices with up to 2 times the performance improvement. Now, following this keynote, we actually have 6 different tracks for you, where you can focus on different aspects of machine learning. Now, if you're more of a builder than a learner, don't worry, we've got some fun activities for you as well. We're going to have a builder zone, we have a deep racer zone, we have hands-on labs, also the ability for you to ask questions to AWS AI/ML experts from around the world. And to cap off this very special event, we have a closing keynote session with Dean Samuels, lead architect for ASEAN, and Olivier Klein, where they're going to have some fun with being more hands-on with the technology. You don't want to miss that. On behalf of all of us here at AWS, stay safe and let's build tomorrow together.